Section 21, Comparing Categorical Variables. A comparatively simple section, but preparation combined with 20 for what we're going to do in 22. So we're back to data analysis rather than inference. And the thing about categorical variables, of course, is there's not a lot to say about them. As we said on the first couple of classes, basically all you have is the categories and the count in each category. So what can we do with categorical variables that is remotely interesting? Well, we can compare categorical variables. You can talk about how left-handedness stacks up to sex or that kind of thing. In this case, I have two variables. One is whether the soldiers in question are stormtroopers or imperial officers, and the other is whether they live or die. So we're back to data analysis, so we're not forming any sweeping conclusions here. We're only studying the data that we happen to have, at least in this section. So of the 3,400 soldiers we happen to be looking at, we can see how they play out. So the way you can compare two categorical variables, that is to say, you've got so many individuals and you have two categorical variables for them, is you can make a two-way table. Simple enough in theory, gets interesting in practice. So this is not that complicated, of course. Of the 3,400 individuals we happen to be looking at, 1,000 of them were stormtroopers who live, 380 of them were imperial officers who lived, 2,000 were stormtroopers that died, and 20 were imperial officers who died. So what can we do? Well, first of all, we can make some totals, of course. How many totals are there? Well, there's as many as there are categories here, as many as there are categories up here, and the total. So this is pretty clear, I think, how this plays out. If we add down, then we see that there are 3,000 total stormtroopers. If we add down, we see that there are 400 total imperial officers. Now again, for a categorical variable, every individual falls into exactly one category. So of the 3,400 total individuals, 3,000 of them are stormtroopers, 400 are imperial officers. In other words, these two have to add up to the total. Alternately, we can go across. We can talk about the 3,400 people and how many lived and how many died. So 1,000 stormtroopers who lived plus 380 imperial officers who lived is 1,380 total individuals who lived. And likewise for the died. If we add up horizontally, then we get 2020 total who died. Well, again, if you add up the total number who lived and the total number who died, then we should get back to the 3,400. As usual, you know, there's the possibility of rounding error if we're talking about millions of apples or something like that, but these are actual counts, so nothing has been rounded here. So, of course, these have to add up to the 3,400, and these have to add up to the 3,400. It's a nice double check, of course. Okay, so let's say that this row variable here is, call it death status, and let's say that this column variable here is, call it soldier type. What can we do with this? Well, first of all, we can talk about marginal distributions. Sounds kind of jargony, but it's exactly what the name implies in this case. It's the distribution over in the margin. The marginal distribution of soldier type, well, here it is. All we're doing is literally ignoring the live-die and taking us back to 3,400 people, whether they're stormtroopers or imperial officers. So we're just amalgamating as we go down. So 3,000 out of the 3,400 were stormtroopers, 400 out of the 3,400 were imperial officers. And if you divide them out, then you have some percentages. And you have, in percent form, the marginal distribution of soldier type. 3,000 divided by 3,400 is 0.88, so multiply by 100 and you get 88%. 88% of those that we looked at were stormtroopers. 400 divided by 3,400 is 12%. Off the top of my head and without checking, I don't remember whether those have been rounded or not. They probably have. Yeah, 0.88235 something. So slightly rounded, but call it 0.88 proportion, 88% stormtroopers. Call it 0.12 proportion, 12% officers. So the marginal distribution of soldier type. Likewise, we could talk about the marginal distribution of death status. We simply ignore the other variable, soldier type, and just look at how life and death plays out. 1380 out of the total who lived, 2020 out of the total who died. So again, we can divide it out. 1380 divided by 3400 is 0.41, so as a percent, 41%. 1380 divided by 3400, 0.40588 something, yeah, call it 41%. Likewise, 2020 divided by 3400 is, well, rounded of course, 59%. Notice, by the way, that it's got to be one or the other, right? So 88% are stormtroopers, 12% are officers. They add up to 100. One or the other, not both, not neither. Every individual falls into exactly one category, so of course they add up to 100%. We'll see some totals here that don't necessarily add up to 100%, but yeah, every individual is either a stormtrooper or an officer. Not both, not neither, so they've got to add up to 100%. Likewise, every individual either lives or dies. Not both, not neither, so they've got to add up to 100%, 41, 59. Then we can ask some relatively basic questions. What percentage of stormtroopers live? So this is all about thinking about what universe you're in. What percentage of stormtroopers live? What do we know for sure? They're stormtroopers. What is in question? Whether they live. So our universe is this column. This is the column in question when we're talking about whether or not stormtroopers live. So the total number of stormtroopers is 3,000. That's what we're dividing by. And the success is living. That's what's in the numerator. So 1,000 who live, 1,000 stormtroopers who live, divided by 3,000 stormtroopers, a third. Call it 33%. What percentage of officers live? Well, you know, that puts you in this column. Now our universe is officers, 380 who live, divided by 400 total number of officers. For sure they're officers, that's our universe. Whether they live is in question. So our universe is the denominator, and what's in question is the numerator, 380 out of 400, which is 95%. Probably exact, but let's check it out. Yeah. What percentage of those who live are stormtroopers? What is our universe? They live. So our universe is now this row. The row of people who live. What percentage of those who live are stormtroopers? So what is for sure? They live. That's our total, 1380. What is in question? Whether they're stormtroopers. So 1,000 divided by 1380. 0.72, 72%. Probably rounded, but yeah, 0.7246 something. Call it 72%. What percentage of those who live are officers? Well, again, you've got your universe of people who live, and what percentage of them are officers? So 1380 divided by, 380 divided by 1380. They're definitely living. It's in question whether they're officers. Numerator, denominator. 0.28, 28%. Now, bear in mind, if you live, you are either a stormtrooper or an officer. So naturally, again, these are going to add up to 100%. I'll say that again. If you live, you are exactly one of stormtrooper or officer. So these have got to add up to 100%. Likewise, you know, we could do this the other way. What percentage of those who die are stormtroopers or officers? What percentage of stormtroopers or officers die, doing the analog of these two questions. So those are just some various percentages you can compute. How to abuse statistics? Well, notice what's going on in this chart. 33% of, let's see, where do we want to be here? Most of those who live are stormtroopers. There you go. 72% of those who live are stormtroopers. Most of those who live are stormtroopers. So, if you want to live, you should be a stormtrooper, right? No, not so much. Officers have a much higher chance of living. If we look here, of those who are alive, 95% of them are officers. We didn't compute it, but the remaining 5% would be stormtroopers. So, of those who live, there's a 95% of them are officers. If we pick somebody who's alive, there's a 0.95 probability that they're an officer. That's the correct way of looking at it. As for the other way of looking at it, most of those who live are stormtroopers. Well, that's true. Most of those who live are stormtroopers. But what did we not compute? What percentage of those who die are stormtroopers? Well, of those who die, 2,000 out of 2020 are stormtroopers, and that also is very high. Let's just take a second to compute it. 2,000 divided by 2020 is 99%. So yeah, the majority of those who live are stormtroopers, but the majority of those who die are stormtroopers. In point of fact, whether or not they live or die, the majority of the people we're looking at are stormtroopers. By far. There's a lot more stormtroopers than officers. So, obviously, most of those who live are stormtroopers, most of those who die are stormtroopers, most of those who were there in the first place, whether they live or die, are stormtroopers. So this is how you can abuse statistics. This is how you can state things deceptively. You have a much higher chance of dying falling down the stairs than you do of dying by standing in front of a herd of stampeding elephants. But you're much more likely to be going down the stairs than you are to be standing in front of a herd of stampeding elephants. It's much more dangerous to be standing in front of a herd of stampeding elephants than it is to be going down the stairs, but there are a lot more people going up and down stairs than there are people standing in front of stampeding elephants. So you see with a little cleverness how you can abuse statistics to make them say whatever you want them to say. But in fact, there is a reality, there is a right way of looking at it, and there is a wrong way of looking at it. Conditional distributions. Conditional distributions are a little trickier, but basically with conditional distributions, what we're talking about are particular rows or columns. So to recap, the marginal distributions is literally what's going on in these margins. Marginal distribution of death status, marginal distribution of soldier type. Well, you can divide by the totals to get some percents. Likewise, we can talk about the marginal distribution here, or here, or here, or here. We can talk about how particular rows or columns are distributed. Sorry, conditional distributions. Marginal for the margins, conditional for the particular rows and columns. So we can talk about the conditional distribution of this row, we can talk about the conditional distribution of this row, we can talk about the conditional distribution of this column, we can talk about the conditional distribution of this column. What can you say about this row? We're talking about people who live. What can you say about this column? We're talking about imperial officers. So in other words, how one variable is distributed on the condition that you happen to be a particular value of the other variable. The conditional distribution of one variable given a particular value of the other. The conditional distribution of x, or whatever it is you're talking about, for whatever row or column you're talking about. Example, we can talk about the conditional distribution of death status for stormtroopers. So if you're talking about how death status is distributed on the condition that we are talking about stormtroopers, then your universe is this column, the universe of stormtroopers, of which there are 3,000. So that's the total you're dividing by. The total number of stormtroopers, that's our universe. What's in question? Which row you're on, whether you live or die. So the conditional distribution of death status for stormtroopers. We're given that you're a stormtrooper. 1,000 divided by 3,000 is the proportion who live. 2,000 divided by 3,000 is the proportion who die. So a third of them, 33% live. 2/3, 66.6 repeating, 67% die. 1,000 divided by 3,000, 2,000 divided by 3,000. That's the conditional distribution of death status for stormtroopers. And so on and so on. Let's look at row 2. If we can get all this on here simultaneously. So if we look at row 2, then we're talking about our universe is those who die, and what's in question is what type of soldier you are. So row 2 gives us the conditional distribution of soldier type for those who die. And if you divide by the total, in this case 2020, you can get the percentages. We've talked about this. 2,000 divided by 2020 is approximately 0.99%, 0.99009900 repeating. So call it 99%. 2,000 divided by 2020, approximately 99%. 20 divided by 2020, approximately 1%. Now again, if you're talking about people who die, they're either stormtroopers or they're officers, not both, not neither. So logically, they've got to add up to 100%. 99%, 2,000 divided by 2020, is the percent of stormtroopers, is the percentage of those who die that are stormtroopers. 1% of those who die are officers. So yes, if you're talking about people who die, there's a 99% chance it's a stormtrooper. If you're talking about those who live, there's a 1% chance it's an officer. Sorry, try again. If you're talking about those who die, then there's the 99% of them are stormtroopers and 1% of them are officers. So you have as many conditional distributions as you can formulate here. You've got conditional distribution for however many rows you've got, conditional distribution for however many columns you've got, and 2 marginal distributions. So there's all kinds of ways you can look at it. This, of course, is only 2 values of the one and 2 values of the other, so it's on the simple side. But of course, you're going to have a lot of categories here and a lot of categories here. You could talk about left-handedness in each of the 50 states. So you've got, let's say, 50 columns and 2 rows, or vice versa. In which case, you've got however many conditional distributions, 52 of them, and a couple of marginal distributions. So that's the idea. Let's take another example. We're talking about a couple of hospitals, and in this case we have some statistics, some data on numbers who lived and numbers who died after an operation. So for Hospital A, 63 of those who had an operation died, and 2037 lived. There you go. For Hospital A, 63 died and 2037 lived, for a total of 2,100 operations in Hospital A. Hospital B, a little smaller, obviously. That may or may not be important. But of the 800 operations in Hospital B, 16 died and 784 lived. And I'm not giving the totals who lived and died in this case because they're not particularly relevant to what I'm going to do. So Hospital B is a little smaller, but that may not have anything to do with anything. It doesn't necessarily reflect how good of a hospital it is, it just happens to be smaller. So let's compute some percentages. Let's look at the percent who die for each hospital. The percentage of those who die after undergoing surgery. So for Hospital A, 63 out of 2,100 patients die. Divide it out and you get about 3%. I'm sure that's rounded. No, it's not. It's exactly 0.3. And while I'm here, the other one is also exact. So for Hospital A, if our universe is Hospital A, then 63 of those in that universe have died after surgery. So depending on how you organize your facts here, depending on what you are inferring, you can say that if you pick one of these individuals, if you pick one of these 2,900 individuals, well, if you pick somebody from Hospital A anyway, then there's a 3% chance you're going to pick somebody who died. You can infer whatever you like from that. There's a 3% chance of dying in Hospital A. We don't know whether these records are typical or not. They might be atypical, they might be cherry-picked, they might be typical of broader realities. In this section, I'm not really concerned with broader realities. We'll talk about that in the next section. But nevertheless, if we're talking about this particular data and picking somebody from here, from these people in question, then yeah, if you pick somebody from Hospital A, there's a 3% chance that pick somebody who underwent surgery at Hospital A, there's a 3% chance that they died. That is to say, 3% of surgeries for the data we have at Hospital A died. Now, if we look at Hospital B, then 16 out of the 800 surgeries there died. So Hospital B, 2%, that's exact as well. For Hospital A, 3% of those who underwent surgery died. For Hospital B, 2% of those who underwent surgery died. It seems pretty clear, right? A is the worst hospital. I mean, in the sense of you've got a higher chance of dying if you go to surgery there. So yeah, it's pretty crystal clear, pretty clear cut. How can you lie about a thing like this? Hospital A loses a higher percent of patients than Hospital B does. In that sense, A is the worst hospital. And that seems pretty conclusive, right? Well, not really. In this, there's always lurking variables. There's always different ways of looking at things. In this case, let's break it up, cell for cell, into two separate cells. From this original two-way table, we're going to relook at our original data. We can't get this from what we have above, but if we look at the original data for the hospitals and look at a lurking variable, a variable that we weren't looking at originally, and this is the condition of the patient. Let's say that, just to keep it simple, and of course it could get very complicated, but just to keep it simple, let's say that there are two types of patients that are about to undergo surgery. There's those who are in good condition and those who are in poor condition. We are lumping together a large variety of things here, right? We're lumping together people who are having appendectomies with people who are having brain surgery. So let's keep it simple and say that the patients who are about to undergo surgery are either in good condition or in poor condition. And then we'll do exactly what we did before. For good condition, Hospital A, of the patients who were in good condition, let's look at this one over here first. Of the patients who were in good condition, there were 600 patients in good condition who underwent surgery at Hospital A. 6 of them died, 594 of them lived. There were 600 patients who were in good condition at Hospital B. 8 of them died, 592 of them lived. Of the patients who were in poor condition, there were 1,500 patients in poor condition in Hospital A. 57 of them died, 1,443 of them lived. There were 200 patients in poor condition in Hospital B. 8 of them died, 192 of them lived. Now notice the way this plays out. If you add cell for cell, you're going to get back to what we had before, right? Hospital A died 6. Hospital A died 57. Total 63. Hospital B died 8. Hospital B died also 8. They add up to 16. And so forth and so on. Hospital A lived 594. Hospital A lived 1443. Well, they're either in good or poor condition, not both, not neither, so they add up to 2037, and so forth and so on. 592 plus 192 is the 784. And of course the totals as well. 600 plus 1500 is the total at Hospital A. 600 plus 200 is the total at Hospital B. Now remember, we're starting all this from the perspective that overall A is the worst hospital. There's no denying that Hospital A has a higher percentage of patients who died. Again, we're not inferring anything, but for the data we happen to be looking at. Presumably these are our available records. For the data we happen to be looking at, yeah, Hospital A has a higher percentage of people dying when they undergo surgery. So let's compute exactly what we computed before for each of these cases. If you're talking about patients in good condition, and again, let's just look at what proportion die. So for patients in good condition, 6 divided by 600 of them died. That's 1%. If you're talking about patients in good condition, then for Hospital B, 8 out of 600 of them died, which is 1.3%. So if you're talking about patients who are in good condition, they have a higher chance, more of them died, a higher percentage of them died in Hospital B. For patients in good condition, Hospital B is the worst hospital. Hospital B has a higher percentage of patients in good condition dying. So if you're in good condition and you undergo surgery, Hospital B is where you have a smaller chance of coming out alive, a bigger chance of dying. So say again, if you're talking about patients in good condition, then 1.3% of patients who are in good condition die after surgery in Hospital B. Only 1% of patients who are in good condition die after surgery in Hospital A. Hospital B is the worst hospital for patients in good condition. What about poor condition? Well, let's do it again. For Hospital A, 57 out of 1,500. For Hospital B, 8 out of 200. 57 out of 1,500 is 3.8%. 8 out of 200 is 4%. So on the one hand, if you're talking about patients in, well, of course, 4% is more than 3.8%. So if you're talking about patients in good condition, then Hospital B is the worst hospital. On the other hand, if you're talking about patients in poor condition, then Hospital B is the worst hospital. Say again? Whether or not you are in good condition or poor condition, Hospital B is the worst hospital. So what we end up with is something that is a little bit strange, almost as strange as the fact that I can't highlight across these columns, but you get the idea. So overall, there's no denying that Hospital A loses a higher percentage of patients after surgery. But whether or not they are in good condition or poor condition, for each of those type of patients, individually, separately, for each of those types of patients, Hospital B has a higher percentage of patients dying after surgery. Good condition, Hospital B has a higher percentage of patients dying after surgery. Poor condition, Hospital B still has a higher percentage of patients dying after surgery. But overall, Hospital A has a higher percentage of patients dying after surgery. What is going on? Bottom line, you're comparing things that shouldn't be compared in the first place. And one brief look at the numbers here will show you that there's something a little screwy going on. You should kind of be prepared for this after the stormtroopers living and dying example. There's a lot more stormtroopers than there are Imperial officers, so everything in this column is swamping everything that's going on in this column. And weird things happen when you do things like that. You can see what's going on if you look at the numbers. If you're in good condition, then you have a 50-50 chance of whether you're even going to hospital A or hospital B. On the other hand, if you're in poor condition, then there is a lot more people going to hospital A than there are going to hospital B. Say again, if you're in good condition, hospital A is attracting about the same number of people Hospital A and B are attracting about the same number of people if they're in good condition. But if you're in poor condition, if you're undergoing major surgery, these are the appendectomies. If you're getting an appendectomy, you don't really care whether you go to hospital A or B. These are the brain surgeries, as it were. If you're in poor condition, if you've got a low chance of coming out of surgery, if it is a serious operation, then there's a much higher chance you're going to be going to hospital A than hospital B. So it's not that hospital A is the worst hospital. It's that hospital A is attracting patients who have a lower chance of surviving surgery. So by breaking it up into the lurking variable, you can see that the trend completely reverses for both categories. In fact, if you've got several categories, this can play out the same way. You can have a trend that goes one way, but then for every one of 7 or 8 or 100 categories, the trend goes the other way. What is going on in this case? Well, it's explained here. A is a medical center which attracts seriously ill patients for a very large reason. If you're undergoing brain surgery, you're going to travel a long way to go to hospital A. B is a small local hospital. It's clearly a lot smaller than A. We see that at the start. B is a small local hospital doing mostly minor surgery. So it's not that you have a higher, the thing to take away here is not that you have a higher chance of dying at hospital A. The thing to take away here is that it's not that 3% is greater than 2%. It's that we're comparing hospitals that have no business being compared in the first place. The real moral here is not that hospital A is worse than hospital B, or that hospital A loses a higher percentage of patients than hospital B. The real moral here is that given the kind of surgery that A is doing, it may be miraculous that these are as low as they are. And given the kind of surgery that B is doing, it may be a scandal that these are as high as they are. So it's not that 3% is greater than 2%. It's that given the kind of surgery that hospital B is doing, the 2% could actually be pretty scandalous. And given the kind of surgery that hospital A is doing, the 3% could actually be very, very low. So you can't compare the numbers directly because of what you're not looking at, the condition of the patient. Now, lest you think that this is all pretty clear-cut, who knows what could happen if we broke it up with another lurking variable and looked at it again. These kind of trends can reverse not once but several times depending on how you amalgamate data. And this is another way that you can lie with statistics. You simply amalgamate categories until they say what you want them to say. There are examples where you can go from level to level to level, breaking up, or if you go the other way, putting together, and the trend reverses not once, but in fact several times. So this is one of the ways that you can deceive people with statistics. Alternately, this is one of the ways that you can make statistics say what you want them to say. This is an example of what they call Simpson's paradox. An association or comparison that holds for several groups can reverse direction entirely when the data are combined to form a single group, or say it the other way, when you break it apart to form more groups. So these trends can reverse, not just for one category, not just for the majority of the categories, but for all categories, which is what we're seeing. Regardless of what kind of surgery you're doing, hospital B is the worst hospital. But because of the things that we're comparing, you can deceive on this level. And again, deceive implies that this is the correct way of looking at it and this is the incorrect way of looking at it. And as far as we can see, that's true. But again, we don't know what would happen if we broke it up further. If we broke it up into something more complicated than good and poor condition, 7 or 8 different types of condition, who knows, it could reverse again. There are some interesting historical examples of Simpson's paradox. The hospital one is the corny one that we usually teach in statistics courses. The Berkeley sex bias case, 1973, gender bias among graduate student admissions to University of California, Berkeley. The admission figures for the fall of 1973 showed that men applying were more likely than women to be admitted, and the difference was so large that it was unlikely to be due to chance. Well, we talked about hypothesis testing. However, when examining the individual departments, 6 out of the 85 departments were significantly biased against men, whereas only 4 were significantly biased against women. So if you look at it on a department-by-department basis, actually more departments were biased against men, fewer departments were biased against women. And as near as I can see from the numbers here, the vast majority don't seem to have been significantly biased one way or the other. What's going on? Well, some departments are bigger than others. Is there a moral there? Yes, maybe, but it may not necessarily be the moral that people were taking away at the start. The different genders were inclined toward different departments. Maybe there's something to take away from that, but it wasn't really relevant for what they were trying to say in the first place. Here's another example. Since 2000, the median wage in the U.S. has risen by 1%, adjusted for inflation. So the median wage in the United States since 2000 has risen by 1%. However, again, adjusting for inflation, over the same period, the median wage has fallen for high school dropouts, high school graduates with no college education, people with some college education, people with bachelor's or higher degrees. That's pretty much everybody, right? Pretty much everybody falls into one of those 4 categories. So regardless of which of these 4 categories a person is in, their median wage has gone down. Now again, if we break it up even further, who knows, the trend could reverse again. There's not necessarily any objective takeaway here. But the point is that the trend that seems to go one way when you amalgamate at one level seems to go the other way when you break things apart and look at it on a different level. And the reason for this, of course, is the numbers, as we've seen in the other examples. There are more college graduates who get higher paying jobs than there were in 2000, but wages for college graduates have fallen at a slower rate than those of the other categories. And so we see different comparative rates, one swamping the other. So we started out with something relatively simple, talking about two-way tables and how we can compute some percents. But nevertheless, there are some interesting takeaways here that we can create when we start talking about different ways of amalgamating data. Simpson's paradox. There's some interesting examples. The other classic example is that I think we've talked about in class. You are more likely to die at sea if you are wearing your life jacket than if you are not wearing your life jacket. However, if you look at the data on another level, good weather, bad weather, if the weather is good, you are more likely to live if you're wearing a life jacket. If the weather is bad, you are more likely to live if you are wearing a life jacket. So yeah, the life jacket is not a bad thing. It's a very good thing. Whether the weather is good or bad, if we look at it on that level, you are more likely to live if you're wearing a life jacket. On the other hand, you've got to remember that most people are not going to be wearing a life jacket in good weather, and there's a lot more good weather than there is bad weather, at least of the you need a life jacket to survive variety of bad weather. So you can have things swamping other things and create very deceptive conclusions with statistics. So how to lie with statistics. It was always the thing that people were mostly going to get out of this course, and at least you can do it intelligently now. So there's section 21. All that leaves is section 22. There's a section 23 in the class notes, but we're not going to include it for the purposes of this course. We'll do section 22, and that'll be the last thing that you're responsible for. Section 22 will take the last two sections and it'll put them together. In other words, we're going to talk about how to do hypothesis tests on things of this nature. The idea is to study whether or not, for instance, being a stormtrooper or imperial officer affects whether you live or die. In other words, we want to talk about whether two categorical variables are independent of one another. Does whether you're male or female affect your chance of being left-handed? That kind of thing. Does which hospital you go to affect your chance of living or dying? And in order to do that, we're going to do some hypothesis tests. We'll take the idea of goodness of fit tests, and we'll throw it together with this idea of two-way tables. So in other words, although section 22 is going to be comparatively complicated, nevertheless, all we're doing is a specific type of goodness of fit test, which is tailored to these two-way tables. So we're going to take the ideas of section 20 and we're going to build on them. We're going to do specific types of examples of them. It just means that we've got to dig a little further to get those expected counts before we do exactly what we did before. And I'll show you how that works in section 22. That'll be our last video, which nobody is watching, and from there we'll be ready to go into the final.